No, it's okay, but we don't hear you. We see your talk, but we don't hear you. Please say something.
He's not on mute.
Okay, I propose to wait a few minutes.
No. No. No.
I'm sorry. Yes, we hear you, but can you tune your microphone?
Hello, can you hear me?
More or less, okay. And please make it slightly louder.
Louder. Okay, I will try. Yeah, sorry for the problems. It
I
seems it
guess
was
now it's okay. Now it's okay. So
okay.
thank you very much. Now we have the last talk. Please go ahead. You have 40 minutes.
Okay, thank you very much. Good evening to everyone. I'm very pleased to be speaker at this very interesting conference, which is organized at the Kurchatov Institute. And you will see in my talk, I will be grateful and I will make homage to a lot of Russian scientists and scholars because a lot of my work is based on previous works by famous scientists. And unfortunately, I cannot be in presence, but I hope in the future it will be possible and I will visit your institute in Portofino and Moscow and will be happy to collaborate and have very interesting discussion. So let me start my talk and today I will tell you something about the quantum conformal theories and in particular those which have conditions of UV finiteness, and this will be also related to the question of asymptotic safety. And all this I will consider in a framework of higher derivative gravitational theories. So we will see all these things together combined. I think I can go to the next slide. So this is very interesting conference. And of course, I'm very happy to be here. I will tell you something about topics related to theoretical gravity, which together mixes the topics from general quantum field theory. Unfortunately, I will not talk much about the experiment or phenomenology, neither about the history or philosophy, but I hope it will be still quite interesting talk for you, and I will discuss these theoretical questions about the construction of quantum gravity theory, which has quite of amazing properties. So let me show you my collaborators. Unfortunately, you cannot see me because I had some problems with the computers, but on this slide, you can see the pictures, the photos of my three collaborators. So first of them is Professor Modesto from Shenzhen in China, in SASTEC, the South University of Science and Technology University in China. And there are two other Russian collaborators, Professor Pinsul, who is now in Brasilia, and Professor Shapiro, who is in the same department as me in Federal University of Juiz de Fora in Brazil. So this is the talk based on collaborations that I did with this famous and very distinguished scientist. And this is based on a paper that archive number and the publication details you see in the bottom of the slide. It was published in PRD, and then you have also supplementary materials in these two archive papers from 2021 and 2022. So this is the group of my collaborators, and now let me put first motivations why we want to have the theory of quantum gravity, which is with higher derivatives. That's something which is extension of the Einstein gravity, but I will try to put motivations why we need particularly this motivation, why we can still stay with metric degrees of freedom, but the theory must be slightly different, must be modified from Einstein-Hilbert. So the idea comes from the seminal work from something like 70 years ago by Utiyama and DeWitt. And the moral is the following. So first, we can consider standard matter theory, like, for example, two-derivative theory, which is very well described by the quantum field theory. And not only we can consider it on a flat space-time, we can consider it also on a curved space-time background, like, for example, in cosmology. And then the following question or following issue arises, that the matter theory produces off-shell divergences, and these are of the gravitational type. And to cancel them, actually to absorb them in a full renormalized theory, you need the counter term of the structure r squared and c squared. So this is something that is very peculiar to 4 dimensions, that we need to add this divergent counter terms. And here you see for the curved space-time background, gravity is kind of fixed theory. I mean, the configuration, the classical configuration is fixed. We do not allow for the moment for the quantum fluctuation of the gravitational field. We have just quantum fluctuations of the matter theory, because that's what we know. For example, standard model of particle physics is a well-behaved quantum field theory when we have quantum fluctuations. So we need these 2 counter terms of the type r squared and c squared, and they have to be added to the divergent part of the matter effective action. And this is particular to the case of 4 dimensions, because they contain precisely 4 derivatives of the metric. So they must be in front of the terms that they are dimensionless. The couplings in front of r squared and c squared, they are dimensionless only in 4 dimensions. So this is very speciality of the 4 dimensions. And this is our conclusion, that we need such counter terms, even if the matter theory, they are of the type with 4 derivatives, r squared and c squared. And this is the conclusion that we can have here if we go first from the quantum field theory with flat space-time, then we go to quantum field theory on curved space-time, and finally, we can allow also quantum gravitational fluctuations. And then it means that we have to use this r squared and c squared terms as the ones which shape the dynamics of the quantum gravitational fluctuations. So it means that we have to study theory which contains higher derivatives of the background metric, but also of the fluctuations. And in particular, in 4 dimensions, we see that there is a good theoretical reason why we need 4 derivatives. The other arguments that was also presented by Professor Mannheim is that when we have the matter theory on a level of path integral and we integrate completely matter fields, then the counter terms, when the theory, the gravitational theory that we are left with is exactly with 4 derivatives. For example, if we have massless fermion or electrodynamics, we integrate it completely when we know that this is preserved with conformal symmetry. So at the end, we have the theory which is while gravity just with the c squared term. This is the result of doing path integral. So this tells us that we should consider higher derivative quantum gravity. And the first model with 4 derivatives was presented by Stella in the year 77 of the previous century. And when you see they are terms with the r squared and with the c squared term, but the one of the Einstein-Hilbert is still there, and we cannot forget it, like Professor Mannheim said in a previous talk. But I want to show you something a bit more complicated, and this was in the spirit of the first paper about general higher derivative theory, and this was done by Azorey, Lopez, and Shapiro. It was written in '96, and this is the general action for the gravitational theory with higher derivatives. It's still a local theory, and it has the cosmological constant term as the first one. Then there's Einstein-Hilbert, and then there is the sum of terms, which I call as quadratic in curvature, because they are quadratic in Ricci scalar, or they could be with Weil tensor. And you see in the middle, there is insertion of the box to the power n operator. And this box to the power n operator is one which gives more derivatives, and all of them, they are summed with some numerical coefficients, and capital N is the order up to which we sum here. And if we consider such theory, we have 2n plus 4 derivatives. So if n is finite, when you have local higher derivative theory, and all these terms with Ricci scalars and Weil tensors, they are here possible. Finally, that's one important thing. We can also have terms which are cubic in curvatures, and they are written here as the last piece of this action, and also higher terms, not only cubic. But for the sixth derivative theory, we will see that from the requirement of total renormalizability, we can have only terms which are cubic in curvature, and they will be important for the developments that I will show you later. So let me tell you what's the plan. So here I want to consider 6 derivative theories. This means that value of the index of summations, the upper limit of summations, n equal 1, and you want to show very similar what was done by Stelle and also other collaborators, that they quantize for derivative theory, for derivative gravity, and they look at the quantum results in particular for the study of the beta functions and normalization group flow. And I will show you the same for the 6th derivative theory. And you can ask why this is good to do this in a 6th derivative, although I said that before we need just 4 derivatives and 4 space-time dimensions. There are various theoretical motivations, and these are all coming from the amazing features of the quantum gravity when you have higher derivatives, more than 4. So if you have 6 derivatives, you can have a better control over divergences. This is the issue of the, as I call here, quantum supernormalizability. And then even if you add these terms which are cubic in curvatures, then you have the possibility that not only you don't have divergences at higher loops, but also that you can completely cancel them at the one loop level. So this is from the point of view of what to do with divergences. So the theory will be in some very special sense, it will be finite. And but then you can ask, so how this result is universal, or how this result can depend on various ways how I make my computation. And amazingly here, as it was a big surprise to them, we have a very powerful theorem which shows that actually the result is universal and doesn't depend on gauge, neither on scheme ambiguities. So there's all these things, they are not present in the divergent part of the effective action, and the beta functions expressions that we will get, they will be completely universal. So they will be free of these ambiguities. And this is a good thing, because what we say about supernormalizability and UV-finiteness, it will be independent on which kind of method of computations we are using. And finally, I will tell you that the results for this theory, when we have the 6th derivative, they are very simple and analytic, and even they are simpler than the case when you have in 4 derivative quantum gravity. Because of course, if you have 4 derivatives, then there's a very special subset of theory which is just with the Weil square tensor, and actually I can tell you this makes the generic 4 derivative theory very special. But now if you are with 6 derivative, we don't have similar very particular theory with conformal symmetry, and that's why we have quite simple and analytic structure. That's what I will show you about the beta functions. So this means that that 6th derivative model that we will consider here is a very good theoretical laboratory to study RG flows in higher derivative quantum gravity. And then it's a model when you can have universal and exact expressions for these RG flows, even if you solve them. So this is something like kind of luxury, but we can have it here because the model is with higher derivatives. So let me just tell you about the theory. So to show you the theory first, I have to show you the action, the classical action. So this is of course the integral of the Lagrangian properly densitized, and in the Lagrangian we can have terms I told you 6 derivatives. So this is one insertion of the box operator between the Weil tensor, another one between the Ricci scalars, and finally for completeness I also write terms which are lower in number of derivatives, so they can 4 derivatives like c squared, r squared. E4 is the Gauss-Bonnet term that I just keep here for completeness, although of course it's a total derivative. And finally, we have also Einstein-Hilbert term with just two derivatives, and the last one is cosmological constant. So this is, let's say, the definition of the theory without terms cubic in curvature, but we can add them, and I will show you which add and with which coefficients. And let me just turn your attention to the fact that you see here for the terms with 6 derivative, we can define a very interesting ratio, which is actually dimensionless. And I call it a fundamental ratio of the theory. It's a ratio between the coupling in front of omega c over omega r. A lot of things will depend just on that. And this is a dimensionless ratio. So you will see that we can basically characterize theory completely by just, I mean, for a lot of properties by just considering the value of this fundamental ratio of the theory. So now let me tell you in this framework of 6 derivative quantum gravity, how we have the situation with the control over divergences. We know that for this, we have to perform some kind of power counting of divergences. Propagator goes like k to the minus 6 in the UV regime because we have the 6 derivative in the action, and the asymptotics of the times in the action between the fluctuation goes like box to the cube. So this was in a first paper by Leonardo Modesto about this super renormalizable theory. And now we can, with this important information, we can construct the superficial degree of divergence. And if you take whatever Feynman graph with L loops, then this is the general formula in 4 dimensions, when L is the number of loops, V is the number of vertices, and I is the number of internal lines. Using the properties and the topological theorem, we can find the following condition on a bound for the delta, which is just dependent on the number of loops. And this is particular for the case of 6 derivative gravitational theory. So we see, for example, that when L is bigger or equal than 4, delta is negative. And when delta is negative, it means we don't have divergences at all, because delta tells you how is the power exponent on divergences. When delta is equal 0, we have logarithmic. When delta is positive, we have power law divergences. But when delta is negative, we don't have divergences. So this is already a signal that starting from 4 loops and higher, the quantum corrections are completely finite. They do not have any dependence on they do not have any divergence. But this is more than that, because you can analyze the structure of the power counting of divergences. And when you see that because delta is bound by 4, we can have only terms c squared, r squared, and Gauss-Bonnet. And these are for the sector of dimensionless couplings. And then, of course, we can have the counter terms proportional to the Einstein-Hilbert term or to the cosmological constant too. But let's analyze the sectors in turn. So the divergences in a sector of couplings with dimension 4, they can receive only contribution at 1 loop, because you see that this bound for L bigger than 2 gives us delta smaller than 2, but then we must have exactly 4 exponents of energy if we want to construct divergences of the type with 4 derivatives. So this means that these terms, they will only get contribution at 1 loop divergent. At higher loops, they will be completely finite. Regarding other couplings, like the one in front of the Einstein-Hilbert term or the one in front of the cosmological term, they receive contributions also at higher level. For example, here we have contribution at 2 loop level, and here at level up to 3. I told you that from the 4 loop level, everything is finite, and we don't have even a divergence proportional to the cosmological constant. So this is one of the consequence of the power counting and the nature of dimension of the couplings. But also, if you come back to the original Lagrangians, the dominant terms are with 6 derivatives. So terms which have the couplings in front of 4 derivatives or 2 derivatives, they do not affect the basic counter terms that I told you here with c squared, r squared, and Gauss-Bonnet. So this is another property of the structure, that basically we will not have influence of the subleading terms, only the leading terms in the number of derivatives. They will shape the form of the divergences proportional to c squared, r squared, and Gauss-Bonnet. Another thing, and that I will come back later, the terms which are cubic in curvature, they can be used to make the model completely finite, so to cancel the beta function such that we will not have any divergent contributions even at one loop. And thanks to super renormalizability, this will be also true for higher loops, for higher quantum loops. So let me tell you about the history of this computation. So first, the divergence proportional to the cosmological constant, they were computed in this famous paper by Azorey, Lopez, and Shapiro. So this was done already almost 30 years ago. Then the divergence is proportional to the Einstein-Hilbert term. We computed in collaborations with Professor Pinsul and Professor Shapiro. This was done 5 years ago. And finally, the most difficult computation is to compute the divergences in front of these three terms because they contain the higher number of derivatives. And this is basically the content of this talk and what I presented previously in the reference of these two papers when there are the results for the most difficult computation, because all the others, they were slightly simpler. So of course, we can use some advantages of the framework that I told you before. So for example, the terms which are subleading, they are not important for the counter terms which are with 4 derivatives. This is the structure due to the analysis of dimension of the couplings. So we can just work in a minimal model. Minimal model means that we have just box between the Weil tensors and box between the Ricci tensors. And the expected form of the one loop divergences is here, that this is just with some constants CC, CR, and CE. And these are dimensionless constants, and they can only depend on the dimensionless ratio of the field. This capital X that I was, calligraphic X that I was presenting before, nothing can depend on the subleading terms, and only the ratio, which is dimensionless, enters, and when we look for the functions of this dimensionless ratio. So this is something that we can kind of very much constrain because of the dimensionality arguments, because of the super normalizability of 6 derivative theory, and we can only ask what are these functions of the dimensionless ratios that we have to compute. Can we understand them a priori? And I will show you at the end, they are not very complicated. So now let me tell you about these other aspects, that we have the independence of the divergent part of the effective action. So in a sense, we have universality of its form. And this is due to famous theorem about the parametrization independence of the divergent part of the effective actions, due to famous 3 Russian scholars, to Kalosh, Tutin, and Tarasov. And let me tell you something about this theorem. There are few observations that we have to make before. The counter term action contains up to 4 derivatives of the metric. This is the result of the power counting. At one loop, we have delta, which at most can be 4. But on the other side, when we take the action of the minimal theory that I presented, for example, here, you can compute classical equations of motion. And these equations of motion contains precisely 6 derivatives. So not 4, but 6. So this is something that is important ingredient for this theorem due to Kalosh, Tutin, and Tarasov, because they show that any change in the effective action, divergent part of the effective action that is computed with some value of the parameters and some other value, some other reference value, is expressed completely by the kind of integral over the equations of motion multiplied by some arbitrary tensor f mu nu, which may depend on the metric, may depend on the initial value of the parameters, may depend on the different value of the parameters. And now let's try to apply it in our case. We know that the divergent part contains 4 derivatives, but on the same side, we know that a tensor of equations of motion, this contains 6 derivatives. So how to make this equality valid? The only way how to make it is that it must be identical to 0. So it means that 0 equal to 0. It's of course possible when we have comparing 4 derivatives with 6 derivatives. And the conclusion is that the effective action, so the left-hand side of this equation, doesn't depend on the parameterization. So you can use whatever value of parameters alpha I 0, or you can use some different values of alpha I parameters, and the results for the divergent part of the effective action stays the same. So this means that we have the independence or universality of the of the results. And here I list what we could think independence of. We can so we have independence of the gauge fixing possibilities, of the choices for the gauge fixing conditions, also of the parameterization of the quantum field, and different choice of the renormalizations. They also give us different parameters, but the difference between the effective divergent part of the effective action is here 0. So it means that this effective action divergent part doesn't depend on this particular choices. So let's take it at use and make the computation here, trying to maximize our freedoms, because we have this independence, so we can choose the gauge fixing in a way that makes our job slightly less tedious, but of course it will be still very tedious. So we want to compute divergences at the one loop. We use the generalization of the Schwinger-David method, and again it was generalized due to two famous Russian scientists, Barvinsky and Wilsonian. So we have the trace technology that we can apply also in higher derivative theory, not only like it was originally done in Schwinger-David only with two derivatives. So the basic idea is to use the trace log formula for the one loop effective action, and H is here the Hessian operator, so it's a second variational derivative of the action with respect to fluctuations. Here we mean the gravitational fluctuations, which are defined by this quantum variable here. So it's a difference from the background metric, and this defines for us a symmetric tensor of the fluctuations. We use this freedom, we exploit the freedom of choosing the gauge fixing such that basically we try to make the Hessian operator as symmetric as possible without the mixing terms. So basically this operator has to be minimal on the level of 6 derivatives. And of course, when we work with the theory with gauge symmetry, we have to remember how to quantize it properly. So another two famous Russians, Faddeev and Popov, they told us what to do with the gauge symmetry and how to introduce ghosts. But here we have higher derivatives, so we have to introduce also the third ghost. That's why we have 3 terms for the effective action. This is the trace log of the Hessian, trace log of the kinetic operator between Faddeev-Popov ghost, and the trace log between the operator in the sector of third ghost. So these are the 3 contributions that we have to sum together, and only in the sum they are gauge invariant and they have the physical sense. Separately, they do not tell us nothing. So this is the idea computations that I will show you the results of. And let me tell you that this is difficult computations because you need to work a lot with symbolic tensor algebra. And for this, we use the Mathematica package to deal with the Hessian and to deal with second variations in the theory of 6 derivatives. So on this level, you may think is a very complicated task, and then the results should be also kind of very complicated. But you will see it will not be really the case. Of course, I will not use the Feynman diagrams because I use this using the covariant trace technology due to Barvinsky and Wilkowski, but the idea is more or less the same, that you want to say what are the quantum corrections to the gravitational interactions, here in a 6 derivative gravitation. So this was just a schematic picture what we want to achieve, and here are the results. So of course I jumped through all the technology of doing the traces, but the results are here on this one slide in 2 windows, when we can compare 6 derivative theory with the 4 derivative one due to stellar, and you will see there is some kind of similarities in the structure. Epsilon is the parameter of dimensional regularizations, X is fundamental ratio, and as I told you, the functions are quite simple, and you see that there is only something in front of C² term. The R² term is in with the numerical coefficient, and the Gauss-Bonnet also is with numerical coefficient. So we have only possibility here to play a bit with the value of the X fundamental ratio, and only in the sector of C² terms in the divergent part of the effective action. So this is the situation in 6 derivative theory. Now let me in brief remind you how it was for the 4 derivative theory, so stellar theory, and this was the computation by Fradkin-Zeitlin and later by Barvinsky and Avramidi, finally with the correct numbers. And you see that the structure is a slightly different, or you can say even complicated, because the coefficient in front of c squared is here a numerical, but we have some quadratic dependence in front of the r squared term. And here you use actually the inverse ratio omega r over omega c. So all the structure can be explained by the fact that I told you if you have the c squared theory, then it's a very special and then it's conformal even on a quantum level. So that's why the structure of the divergences in generic stellar theory must reflect this complicacy. And that's why we see, for example, the x prime dependence only in front of the r squared term. But let me put another comment from another type of the game. It was already noticed by Codello and Percacci that if you take this four derivative theory, you look at the one loop, and because of course here you have contributions also at higher loops, you cannot have a full UV finiteness because you can only play with the value of x prime parameter. So you can maybe make the sector r squared finite, but not all the others, because the others, they are with some constant coefficients. So this means that in stellar theory, we cannot have a full UV finite theory. And now the question is what we can say about the sixth derivative theory. Can we have there? So let me just write the form of the beta functions, and later we will easily solve them. So this first three for the dimensionless coefficients, they are exact. And I told you, they do not, they depend only on numerical constant. They do not depend on the constant that is running. So for example, theta r is a constant that we follow RG flow, but it doesn't appear on the right hand side of the flow equation, because the flow equation depends only on the dimensionless ratio of the six derivative terms. So this is the exact part. We also have from the previous paper, I told you, the running of the G Newton, and from the paper by Azoray, Lopez, and Shapiro, we have the computation of the running of the cosmological constant. These subleading terms with less number of derivatives in the divergent part of the effective action, they do depend on a couplings omega r and omega c, but consistently we can make them also equal to zero, such that these beta functions of the cosmological constant and of the Einstein term, they are also can be chosen in such a way that this sector doesn't run. And we can easily find a solution, because I showed you the equations, differential equations for the RG flow. They are linear and they do not have this feature of they are not coupled to each other. They are just separate equations. We can very easily integrate them out, because this gives us just linear function t. T is the logarithmic RG time. And it's important to analyze the initial value and the sign of the initial values for this flow equations. For the last two, running of cosmological constant and running of G Newton, we have the dependence, which is up to quadratic and cubic in a terms with the logarithmic RG time. So condition for the asymptotic freedom is that at least here theoretically we would like to have that there is no meet of the Landau pole in the UV regime. So here, unfortunately, the famous Russian scientist Landau appears not in a very good spirit, because we don't want Landau pole. So of course, this is something that we want to avoid. But of course, all the other contributions of Landau, they were very great. So to avoid the Landau, which could scare us in the UV, we want to have that theta r is, for example, negative, because the sign of the beta functions in front of theta r is also negative. And the same we can do with the coupling in front of the Gauss-Bonnet. We can ask what's the situation in the sector of the c squared term, and when there's a particular value which makes the sector very non-trivial, and then it means that if we stay with this particular value, then we are at the asymptotic safety. So now let me tell you what is this particular value. This is the ratio which is mentioned here, and this is exact numerical value which defines for us a non-trivial fixed point. Non-trivial fixed points means that beta is equal 0, so we have a condition for the asymptotic safety. The value of the parameter theta c is here arbitrary, so on a full parameter space we have one-dimensional line of fixed point. So this is the situation that we can have only for the c squared sector, but the good question is, can we have it for the full sectors, not only of c squared divergences, but also of r squared, and in front of the Gauss-Bonnet, then we would have a full UV finiteness, and also this will be tantamount to having full asymptotic safety in the model of 6 derivative. So let me just tell you what this would also imply, because we will have beta functions equal 0, so we have scale invariance, and this can be promoted to conformal invariance. And this would give us an example of a consistent quantum field theory when we have conformal symmetry at the UV fixed point of the normalization group. So we will stay there at the fixed point. We will not have any running, but we will have a conformal symmetry. So for example, we will have vanishing of the trace anomaly because all these coefficients, they are proportional to the beta functions. And on the other side, we can say that the conformal symmetry is important because, for example, we can resolve the singularities, like the classical GR singularities in the center of the black hole and also at the beginning of the universe. This is because we can do the rescaling, and when the singularity appears only in the artifact as artifact of the conformal factor. So this is something that we can see, and generally conformal symmetry is very useful in quantum field theory because it puts a lot of constraints. There are famous examples, and in the case of the gravity, this was done by again two famous Russian Fratkin and Zeitlin when they constructed n=8 conformal supergravity. So this is a very special model when you have the situation when you are sitting at the UV fixed point. But generally this part that you have conformal symmetry in a gravitational theory, this means that you have a lot of symmetry, and this is useful because, for example, the effective action is very constrained. The dimensions of anomalous, the anomalous dimension of operators, this is the only thing which is basically there, because we don't have running, we don't have beta functions, only finite renormalization of couplings, and we don't need the scale lambda to put in our effective actions. Everything is only with finite corrections. And then we know that this conformally symmetric phase can be a basis for studying of various deformations in this model of quantum conformal gravity. So now let me see if we can achieve it here. So for this, we need terms which are cubic in curvature, and they are still allowed by the effective field theory. And this is the sequence of all of them, and that are independent in 4 dimensions. We have exactly 6 of them. And they are still allowed because if you add them to the original Lagrangians, they do not destroy the renormalizability, they do not destroy quantum super renormalizability. Everything can be still within the same framework. Now the only fact is that the structure of the beta functions will be more complicated. Basically, it will be some quadratic form in this coefficient in front of these terms which are written here for completeness. And for example, we can find some examples of when this UV finiteness is realized in all the sectors. So this is some numerical solutions when you have relation between the couplings of the theory and some selected values of the coefficients in front of all these 6 terms. You see at the end there are some numerical values. But also, let me show you, there is a whole system that you can write here, and this is quite...
Sorry for interrupting. You have only 5 minutes.
Okay, yes, yeah, I will be close to my conclusion. So this is the system of beta functions that you can have in this system. I told you it's quite complicated algebraic system for quadratic equations. And now let me tell you what we can see here. So if we want to put this condition that all the 3 beta functions are equal to 0 in the sector of dimensionless couplings, then you know, we just require, I mean, algebraically, it would be always possible to solve if you are working in a field of complex, but here we want that the couplings and the dimensionless fundamental ratio of the theory, they have to be real. So this is the condition that we have to impose for our quadratic equations for the conditions for vanishing of all 3 beta functions. So it means that, for example, 3 quadratic discriminants, they have to be equal to equal or bigger than 0. And this means that we have some kind of problems or a kind of interesting issue in the solution for the algebraic inequalities, which is the intersection of 3 three-dimensional regions. So this is maybe difficult to visualize, but that's what the condition for asymptotic safety and for UV finiteness tell us. And for example, the precise analytic analysis here of the structure of the solutions show us that there is excluded region. So not all the values of the X parameter give us UV finiteness with real coefficients. If the coefficient is between 20, more or less 21 and 1192, then you are not able to find. This is kind of big window that is excluded. But in this region, algebraically, we are able to show that there doesn't exist solution with real coefficient. So this is something that already constrained the value of X. And the example that I showed you before was with X equal 1. So of course, it's without that window. But you have to be careful that algebra here can give us some conditions that we have to preserve. So now let me come to the part of the conclusion. So I showed you some model of 6 derivative gravity. It's a very famous and very amazing situation because we have quantum supernormalizability. So we have better control over divergences. And even if we add terms which are cubic, we can have complete situation with UV finiteness. The expressions for the beta functions that we found for the dimensionless couplings, they are exact and universal. They do not depend on neither on the gauge nor the parameter independence, how you define the quantum fields. And then we are able to solve the exact RG flow equations and put conditional asymptotic freedom in the sector of UV. I told you that asymptotic freedom is a good thing because when you avoid the Landau pole, but also the other thing is asymptotic safety when you are sitting all the time at the UV fixed point, non-trivial UV fixed point of the normalization group. And this is all related to the conformal symmetry, which is very powerful on the level of quantum gravity with conformal interactions. You can have the very conditions for this case when you have UV finiteness, and this means that you have to add operators which are cubic in curvature. And I showed you the dependence that not all the values of the fundamental ratio they are allowed. Some values are excluded, and this is important, for example, for the construction of the models when you want to have the UV finiteness in this framework. So now I put the reference to other works, and you see there is a lot of Russian collaborators and also a lot of papers that I wrote before, and they are based on a seminal works by other famous Russian scientists. So I think now it's a time to thank you. I can say spasiba. I can also say in my original language, dziękuję, and obrigado in Portuguese, since now I come from Brazil. So this is, I think, last slide of my presentation. So I want to thank for your attention, and I'm open for questions. Thank you.
Thank you very much for the very interesting talk. I see one hand, Philip. Are you going to put a question?
Yes.
Okay.
First of all, Leslaw, nice to meet up with you again, and I enjoyed your talk. I have 2 comments. One is only peripheral. That is, you had noted that if you take a fermion coupled to the spin connection and you do the path integral over the fermions, you generate a 4th order theory. And that's a very strong argument for higher derivative theories being relevant to physics. But it also tells you that there can't be a ghost, because integrating out the fermions in a path integral is equivalent to a one-loop Feynman diagram. And since the standard model didn't have a ghost before it was coupled to gravity, it can't generate a ghost when it is coupled to gravity, and therefore gravity must be ghost-free. Therefore, there has to be a solution to the ghost problem, and to think that there might be a ghost is really just not correct. And that's what Carl Bender and I had discussed by showing that you simply were in the wrong Hilbert space. Now, the other issue actually relates to that. You discussed the Lee-Wick realization. Now, it turns out that if you have an antilinear symmetry, for every energy E, there must be an energy E star. So energies are either real or in a complex pair. What I proved was the converse, that if the energies are real or in a complex pair, there must be an antilinear symmetry. So that means that the Lee-Wick realization, which preserves unitarity, is due to the antilinear symmetry. But the same antilinear symmetry tells you that if you simply had real poles, namely 1 over k squared minus m1 squared minus 1 over k squared minus m2 squared, you were already unitary. And you just were, it didn't appear to be unitary. So those are the comments.
Yeah, so thank you, Professor Mannheim, for your Nice comments. Yes, I fully agree. Unfortunately, in my talk, I only tangentially mentioned this issue with unitarity and Lewick theory, but of course you're right that when we integrate fermions, the original theory is unitary, so we cannot destroy that. And this is a very strong clue that yes, there must be a way how the theory, even with gravity, is unitarity. So of course I fully agree with you. And yes, this comment about Lewick is of course also very important. I can just tell that yes, I mean, here there is one famous paper by Modesto and Shapiro, and they discuss this Lewick. But I think that yes, your input and your insight is also very important here. That this is what you proved with your theorem. So yes, I mean, we completely agree. The only thing that we could kind of maybe analyze, but I think it confirms your findings, is that yes, the pair of Lewick, they have a very special properties, and you have to check whether this is not invalidated by one loop corrections. And I think we have some preliminary analysis, but it shows that yes, it is not invalidated. So basically, this statement about antilinear symmetry is also present on a quantum level. So that's a good thing. That as I told you, it verifies that of course your theorem is right. We just check it on a one loop level.
Yeah, I think you don't have to worry about the two loops, because in general the antilinear symmetry is CPT. So unless radiative corrections destroy CPT, you're guaranteed to have a Lewick in higher order.
Yeah, that's a very good comment. Yes. So we are not worried about second loop. Yes, and then we would assume, or we would like to have, that CPT is not violated. Yes, of course.
Thank you very much. I think we transit to the general discussion. The leader is Vladimir Solovyev. Please go ahead.
Well, we had a great day. We had 12 talks today, and almost all of them were interesting. And I would like to thank at first all the speakers for these talks and all the listeners for their attention.